Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. I'm Dr. Owusu. In today's session, we will be continuing with our practical work, should I say, virtual practical work. We have been doing a series on practical chemistry and the required practicals on the OCR A-level course. And in today's episode, we're going to be looking at research skills. So we're going to be looking at all the skills and competencies you need to be able to carry out an open-ended investigation in chemistry. As usual, we will be illustrating the points that we make by tackling some practice questions to reinforce the points. And at various points during the lesson, I will be pausing to take any questions you've got. Please do use the chat function and do drop me a line if you've got any questions at all. And of course, before we start, I will be sharing my tablet with you so that you can keep up with what we are working through on screen. So do bear with me a few seconds while I connect my tablet and we can make a start. Brilliant. So you should be able to see my title screen, which says Practical Chemistry and Research Skills. We're looking at Practical Activity Group 12 and all the skills and competencies required to carry out an open-ended investigation. We will be doing this in the context of finding out the amount of iron in iron tablets. So you can imagine the scenario as having 4 or 5 different brands of iron tablets and being charged with finding out how much iron there is in each brand of iron tablet and therefore verifying what the manufacturer has said is in their tablet. We'll look at all the skills that are required to be able to carry that out successfully, get accurate results, and to show all the hallmarks of a good scientific investigation. That is one that can be reproduced by others using the same method that you've used and get the same results. Okay, so practical chemistry and research skills is what we're looking at. Brilliant. So a good place to start, as always, is your specification and what it actually requires as far as practical activity group 12 is concerned. And as you can see there, it's talking about research skills, and it breaks it down into 3 key areas, and these are shown over here in this column. And the first is to apply investigative approaches. And you might wonder, what does that mean? We'll look at that very shortly and break that bullet point down into its constituent parts. We're also going to be required to use online and offline research skills. So you may already, I'm sure you're all familiar with this already, being able to find a good source of information to support any research you're carrying out and being able to cite that source appropriately. That source, of course, can be in the form of an online website or web page or blog or an online encyclopedia. It could also be in the form of a published sort of article in a journal. You could have a hard copy of it, so that would be offline, something in the library. It could be your textbook. And so being able to use a combination of sources from both sort of realms, online and offline, is an incredibly important research skill. And being able to cite these sources that you quote from is a key part of scientific research. And that's what the third bullet point talks about, correctly citing sources of information. Okay, so those are the 3 key points. And as I did allude to at the beginning in my introduction, we will be looking at research skills in the context of iron and iron tablets. And the relevant area of chemistry is, of course, redox chemistry and transition metal chemistry. Of course, transition metals have a key part of the way transition metals behave is the redox properties and the variable oxidation states. So that is the scenario we're going to be looking at. Of course, all these research skills have got all sorts of areas in your specification that they apply to. So there are opportunities, not just in redox chemistry, but in all areas of acid-base chemistry, thermodynamics. So the list is endless. So we're going to be looking specifically at redox chemistry of iron in applying our research skills. Okay, so that's a general overview of research skills, we now want to look in a bit more detail at what is required when we're asked to apply investigative approaches. Okay, so I have again taken this straight from your specification. You should be sort of getting yourselves familiarized with the specification and exactly what it requires of you for different areas of the course. Okay, so applying investigative approaches and methods when using instruments and equipment. So what does that actually mean? So choosing the appropriate instrumentation, choosing the correct sorry, the word escapes me. The correct instrument, I guess, is what we want to say. So choosing the correct apparatus and using the correct materials to allow you to get an accurate answer, to allow you to find out exactly what it is you're after. Okay, so the apparatus and materials to carry out your investigative activities, choosing the correct techniques, the correct methods for to allow you to get accurate results is also important. And being able to do so without sort of the help of your teacher is what is required at this stage. So remember that PAD 12 is something that you would be tackling sort of towards the end of the A-level course. So you'd have had a lot of practice of lots of different techniques, and you'd have had quite a lot of guidance in using those techniques and using the different pieces of apparatus. And so by the time you get onto PAD 12, you should be feeling confident that you can independently put all of these skills together and use this skill set to then answer an open-ended question to an investigation of the sort we're going to describe today. Okay, so that's part A. And part B says to carry out techniques or procedures methodically, in sequence and in combination, identifying practical issues and making adjustments where necessary. So being logical is important. Now imagine, for instance, in organic chemistry where you're being asked to identify 4 unknown liquids and you're being asked to carry out tests to identify them. What you want to do is to carry out a series of chemical tests in a logical progression so that you positively identify all of the compounds present. Okay, so for instance, you might have a mixture of alcohols and ketones and aldehydes, and you don't know which one's which. It is important that at the very beginning, you pick one test, say you use Tollens reagent, and you test all of your unknown compounds using Tollens reagent, and thereby eliminate the aldehydes, but positively identify the aldehydes as a result. So once you've identified one of the 4 unknowns, you can set it aside, and then in the next step, you're going to pick another chemical test, which you will apply to the remaining 3. So that's a logical, sequential sort of application of the different sort of methods you would need to get to the final answer. So that's what B is interested in, being able to carry out techniques in a logical, sensible way. Now, in part C, we're asked to show the ability to identify and control significant quantitative variables where applicable, and be able to plan an approach or take an approach that takes into account the variables that cannot readily be controlled. Okay, so sometimes you do have to sort of make do with a plan that is sort of not able to sort of control for all the variables. So you want to control the variables as best as you can. So only one variable is being changed at any one time. Right? So for instance, if you're doing a clock reaction where you're changing the concentrations of one particular reactant, you want to make sure the concentrations of all the other reactants are kept constant. And the way you do it is perhaps by making up the total volume always to the same volume by adding appropriate volumes of water, for instance. It may be that in doing that practical, you don't have a suitable enough means of ensuring that the temperature at which the reaction is done is absolutely constant. But we can assume, for instance, that the room temperature is sort of almost constant, doesn't vary much at all. It's very unlikely that in the course of your investigation, someone would come along and turn up the heating so that suddenly you've got a much hotter room than you started off with at the start of your practical. Okay, so those are some of the variables that we would perhaps need to control, some of which are more easily done than others. Okay, so that's point C, and then point D, we're told, is to show the ability to select appropriate equipment and measurement strategies in order to ensure suitably accurate results. So, for instance, if you're measuring the mass of a reactant to use, or the mass of a salt to use in a standard solution, you want to measure that mass by subtraction. Okay, so measuring the mass of the weighing boat and solid together, transferring the solid into your reaction flask or the beaker, and then reweighing the weighing boat so that you know the difference is what's actually been transferred into your flask. So measuring by mass by subtraction means that you have a more accurate value for the mass you're actually using. Okay? So using strategies like that is important. Selecting appropriate equipment. If you're going to be carrying out a titration and you want accurate results, then you want to measure your volume with a pipette, a glass pipette, and you want to measure your titer values or titer volume using a burette. Okay, so these are the instruments of choice because of the small error in using those particular pieces of apparatus compared to, for instance, a measuring cylinder, say. Okay, so these are all things that will be assessed, that your teacher will be looking at, and so you want to make sure that in carrying out this investigation, you think about all of this in your planning, and it is important that you plan before carrying out your investigation. So start with research, and then planning, and then to executing your investigation. Okay. And also a little bit about using online and offline research prior to carrying out your investigation. And this sounds sort of fairly obvious, but you are going to be using your computer, you are going to be using your tablets, or you are going to be using your textbook to do research, and in the course of that research, you're going to be citing the sources of information, and we'll look at the different ways of citing your sources and putting down your references very shortly. But another important aspect of sort of researching, referencing, and reporting is being able to process the data. Right? So let's say you carry out a series of titrations and you get a series of titer values. How are you going to use those titer values to, for instance, calculate the mean titer properly? Okay, are you going to pick just concordant results, or are you going to be using all your titer values? So that is a test of your ability to use the data that you generate properly. Okay, so using appropriate software and or tools to process data. Again, if you're doing an acid-based titration, you could, for instance, use an Excel spreadsheet to allow you to plot out your titration curve. For instance, if you're doing a weak acid, strong alkali titration, you would need some different formulae in different cells for when you've got a weak acid at the start, when you do have buffering not long after the start, and then when you've got an alkaline solution after you've gone past the equivalence volume. So quite an intricate piece of work involving Excel in that instance. So that would be pretty appropriate to use software of that nature. Okay, so let's sort of get down to business and the actual investigation we want to look at in today's session. And the question there is, how much iron is there in an iron tablet? So you've got 4 or 5 different brands of iron tablet, and we want to know how much iron there is in there. We want to check the manufacturer's claims that they've got maybe 80% by mass of iron in each tablet. So how are we going to go about doing this piece of investigative work. And the first point to start with is research. Okay, so what is in an iron tablet is an obvious but important question to ask. Okay, so is your iron tablet entirely made of iron? Probably not. Very unlikely. Okay, so what's in an iron tablet? You might need to do a bit of research, and in doing that research, you might find out that your iron tablet will contain perhaps iron 2 sulfate, so FeSO4, and it's usually hydrated, so have water crystallization in it. It might also contain a bulking agent, so something that makes your tablet a bit bigger so that it's not so tiny that it's very difficult to take or pick up and sort of swallow. So you might find that a lot of tablets or pills will have a bulking agent. You might have something that binds the iron compound to the bulking agent. You might have a binder in there. Okay, so these are all things that go into making up the bulk of your tablet. So your tablet doesn't just contain the active ingredient, it contains other things. It might have a sweetener in there as well, so that your pill isn't so bitter. If the active ingredient in your pill is really bitter and makes it difficult for people to take the medicine, then you might sweeten the pill. And that's where that saying comes from. Okay, so lots of different things that you might find your iron tablet contains. Okay, so you're going to do that research, and whatever you find out, you do need to reference, and you need your citations to say where you got the information from. And we'll look at how you do that very shortly. Okay, so we know that there is iron 2 sulfate in our iron tablet. You might also want to research why we take iron tablets in the first place, because iron is incredibly important for our red blood cells. It binds to oxygen. The red blood cells transport oxygen all around the body, and so we can't afford to be iron deficient. So if you're iron deficient, you've got anemia. So to combat anemia would be the predominant reason. Okay, and different people are susceptible to anemia. So perhaps pregnant women might need to take iron tablets, or perhaps someone with sickle cell anemia, where there is a red blood cell disorder, might need to take iron tablets as well. Okay, so it's a very important, very low cost, but incredibly important medicine or supplement, you might even say. Is there a qualitative test for the iron present? So how do we know that there's iron present in these pills at all? Perhaps you might want to do a qualitative sort of assay or analysis where perhaps you add some aqueous sodium hydroxide to a solution of your tablet that you ground up and dissolved in perhaps sulfuric acid, and see what you get as a result. So you could perhaps add I guess so you could add your aqueous sodium hydroxide to the solution possibly containing your Fe2 plus ions, and if there is any Fe2 plus present, you would form a precipitate of iron hydroxide, which can, in this instance, be a very sort of pale green color. Okay, so yes, there are qualitative tests. How do we quantify how much iron there is? And this is the key part of our investigation, to show how much iron there is. How do we quantify it? How do we work out the mass of iron in our pills? You're going to be needing some sort of redox titration here. So you're going to be needing to work out how much iron, Fe2 plus, there is by reacting it with an oxidizing agent. So we can, if we can measure accurately how much oxidizing agent we've used, we can then use the molar ratio between the oxidizing agent and your Fe2 plus ions. So in other words, looking at redox half equations and combining them to get a molar ratio. And that allows us to work backwards to see how much iron was reacted in a given volume. And then we can work back up to see how much iron there is in your standard solution that you've made by grinding up however many tablets, and you can work out how much iron there is per tablet. Okay, so some sort of I think, fairly straightforward, but quite a lengthy series of calculations you need to do, a series of calculations that you need to do to get back to the iron in your tablet from your redox titration. And we'll look at exactly how to do that. And as I said in the introduction, if we're looking at 4 or 5 different tablets from different manufacturers, is there going to be variation in the different tablets? Do some manufacturers have more or less iron in their iron tablets? And perhaps you might want to go off and find out why there are different doses, for instance. Okay, so that's the question we're addressing. Before we look at the chemistry itself, let's look at referencing and the two main ways of referencing any sort of research you do and any report that you write. My preferred method is one that's, if we use my laser pen instead, that's the Vancouver system, which is shown here, which is what most chemistry journals have. So as you're writing your report, if there is a point that you make that needs to be cited, you will give that a number. And then at the end of your report, in your bibliography, that number will have the full reference. So if we read this part here, titrations using potassium manganate 7 can be used to determine the concentration of solution of Fe2+ ions. Okay, so that's a statement of fact. That's not your own discovery, it's other people who've discovered that. So you've got to say who has done the work to show that you can actually find out the concentration of Fe2+ ions using a titration with potassium permanganate or potassium manganate 7. So 1. And then at the bottom of your document, you've got the full reference there. Joe Block's blogs 2011, manganate 7 titrations, 2nd edition, Cambridge, practical chemistry publication. Okay, so that's the Vancouver system. That's my preferred way of doing it. There's no one way of doing it. The important thing is that all the information needed for a reader to go off and find out about the original work itself has to be there. And of course, the other is one that is more common in the arts and humanities, but it can be used in science as well. It's called a parenthetical system, or the Harvard system. So titrations using potassium manganate 7 can be used to determine the concentration of the solution of Fe2+ ions. And then you get a very abbreviated form of the reference. So instead of having a number, you just say blogs 2011 there. And then at the end of your document, you're going to have the full reference. So blogs 2011, manganate 7, titrations, and so on. But you would have the names of the authors in alphabetical order. Okay, so that's the difference. Both are fairly straightforward to follow. It's a case of a matter of what you prefer out of the two. So referencing is incredibly important, but something that many students seem to think isn't and disregard. As a scientist, you'll find out when you all go up to uni and start perhaps working in research and producing scientific papers, you can't sort of not use sort of adequate references or citations. If something isn't your own original work, and that includes work that you've done previously, you do need to cite it. You need to cite the original piece of work. That's very important because readers have to know what your sources are if they're going to be verifying your work. Okay? Right, so we're looking at how to work out how much iron there is in an iron tablet, and that means we need to look at some redox chemistry. Now, I've got the 2 redox half equations we need already written down, but perhaps it would be a good idea to show you how I arrived at these 2 redox equations. So I'm going to erase them and we'll start all over again. Okay, so we know that there is Fe2+ in our iron tablet, and we're going to be oxidizing that Fe2+ to Fe3+ using potassium permanganate or manganate 7. Okay, so our Fe2 plus is going to Fe3 plus. That's a starting point. Now, Fe2 plus must have lost an electron to become 3 plus. So that electron is going to be on the right-hand side to show that it is or has been produced as a result of Fe2 plus losing it. Okay, so Fe2 plus loses that electron, and to check that we've got a balanced half equation, we've got 1 mole of Fe and 1 mole of Fe there, different charges, and so we need to make sure the charges are balanced by having that electron there. So 3 plus and 1 minus means you've got a total of 2 plus there, you've got a total of 2 plus there. We've got a balanced half equation. Okay, so that's our iron, that's what's happening to the iron. It is being oxidized. Okay, so we can perhaps annotate that, say Fe2 plus is oxidized. Now, if Fe2 plus is being oxidized, something else must be being reduced. Of course, that is our manganate 7, MnO4 minus, which is itself being reduced to Mn2 plus ions. Okay, and how do we complete that redox half equation? We need to introduce oxygen to the right-hand side. That would require 4 moles of water, so that we've got 4 moles of oxygen atoms on the right-hand side. And because we've got hydrogens on the right-hand side now, we need to introduce H plus ions. Acidified manganate 7 is what we're going to be using. We're going to need 8 H plus ions. The 8 H plus ions are as a result of our 4 moles of, or rather 8 moles of hydrogen atoms in the water. So here's our 8 H pluses. We're not quite done yet, because even though all of the elements are balanced, we've got the same numbers on both sides, the charges are not balanced yet, so we need to balance the charges. We've got a total of plus 7 on the left-hand side, so 8 pluses and 1 minus, so that's plus 7. We've only got plus 2 on the right-hand side, so we need to bring this side down to plus 2. And the way to do that is by adding electrons, 5 electrons to this side of our half equation. Okay, so those are 2 balanced half equations, and what we can do is combine the 2 to get an overall redox equation, and that would then give us the molar ratio between iron and manganate. Okay, so how do we combine the 2 half equations? Well, we need to consider the electrons. The oxidation equation is producing 1 mole of electrons, but the reduction equation needs 5. So let's complete things by labeling. That is the reduction equation. And so we need to multiply the oxidation equation, that one there, by 5. So if we do that, we would then get an overall equation which would be 5 moles of Fe2 plus reacting with 8 moles of H plus ions and 1 mole of MnO4 minus, producing 5 moles of Fe3 plus and Mn2 plus and 4 moles of water. Okay, so what we're looking at is the molar ratio between our Fe2 plus and our MnO4 minus, which is 5 to 1. We need to check that the charges are the same on both sides, otherwise we don't have a balanced equation. So we've got 10 pluses, another 8 pluses, so we've got 18 pluses and then 1 minus, so we've got 17 pluses there. 5 times 3 is 15 pluses and another 2, so 17 pluses on both sides. So we do have a balanced equation. Okay, so we need to acidify our manganate 7. What acid are we going to use? The choice of acid is incredibly important. You can't use HCl or HNO3. HCl can't be used because it will reduce your permanganate So you don't want your permanganate reacting with your chloride ions. You want your permanganate to be reacting with your iron 2 plus ions. Okay, so can't use, so will react with or reduce Cl minus or reduce or manganate. Okay, so we don't want that. So nitric acid, on the other hand, is a very good oxidizing agent. So will oxidize Fe2 plus. Again, we don't want that. We want MnO4 minus to do the oxidizing because it's got a color change for the endpoint that we can use to determine when to stop our titration. So if we have nitric acid present, that will be adversely affected. If we have chloride ions present as well, that would be a bad thing, a no-no for our titration. Okay, so the acid of choice is going to be sulfuric acid. So sulfuric acid is going to be used to acidify your manganate 7 or permanganate, and you want to make sure that you have a large excess of our sulfuric acid, because if you don't, you're not going to get manganese 2 plus. You're going to get manganese oxide, which is MnO2, which is manganese plus 4. That forms a brown sludgy solid, and again that obscures the end point of your titration, and it means that you're likely to use too large a titer volume, or they're called too large a titer volume, which of course would be inaccurate. So have a large excess of to ensure Mn2 plus is formed and not MnO2. Okay, so that's what we're going to be doing as far as the chemistry goes. So in terms of the practical itself, I've got a little image here to show you what the titration looks like. So you've got your potassium permanganate, which is that purple solution in your burette, and in here you will pipetted your solution containing your iron 2 plus. Now, as you add your purple potassium permanganate, it hits your solution of Fe2 plus, it reacts, and the solution remains colorless until there's no more iron 2 plus in there. As soon as there's no more iron 2 plus in there, the permanganate that arrives in the beaker has nothing to react with, and so it just stays purple. So as soon as you see the first permanent purple color, you've reached the end point of your titration. So we don't need an indicator for this titration. It is self-indicating. You get a color change when there is no Fe2 plus left in your solution to react with your potassium permanganate. Okay, so it is a self-indicating titration. In terms of the equipment needed, you've got all your standard lab equipment, and you've got 5 iron tablets you're asked to grind up into a powder. If you use just one, there'd be a very small quantity of solid. It means that you would have larger errors in sort of measurement of mass, for instance. So use a large enough mass of your iron tablets. You're going to be grinding it in make this a bit bigger. You're going to be grinding it in a mortar and pestle, and you're going to be dissolving it in sulfuric acid. You're going to use 1 molar and an excess of sulfuric acid, and you will need, amongst other things, distilled water. You will need to make up the volume to the mark. If you're making a standard solution, and you do have to make a standard solution of your iron 2 dissolved in your acid. You do have to make it up to the mark in your volumetric flask. You're going to do that with distilled water. You're going to use a volumetric flask. And if we burettes and volumetric pipettes, filter funnels, because a lot of the bulking agent in your pill will be insoluble, so you will probably find that you need to filter it. And then, of course, potassium permanganate solution and various sizes of conical flask. Okay, so in terms of the method used, you're going to grind up your iron tablets, 5 iron tablets, and you're going to place the tablets into a weighing boat and accurately measure their mass. Accurate measurement of mass is by subtraction. So mass of solid and weighing boat, transfer solid into your beaker or conical flask, and then reweigh the empty weighing boat so that you know exactly what has been transferred in terms of mass. Okay. In step 3, you're going to add the iron tablets into your 100 centimeter cube conical flask, and you're going to add 50 centimeters cube of sulfuric acid. You're going to stop the flask and shake it so that your tablet completely dissolves. Remember, you will get some material that does not dissolve because, for instance, you've got bulking agents, often very large sort of starch-like molecules that will not dissolve in your acid or water. So you want to sort of filter that. Okay, so you're going to leave the solution for a while until the residue, so that's what we've just been talking about, has settled. And then without disturbing the residue, so carefully filter the solution directly into your volumetric flask. You're going to rinse the residue in the filter paper with a small volume of water to make sure that you're getting all the Fe2 plus out. And then you're going to add sulfuric acid to make the solution up to the mark of the volumetric flask. Okay, so once you've done that, you can then convert your volumetric flask several times to ensure that everything is uniformly mixed. And then for the burette, you're going to wash it or clean it before using it. Rinse it with your potassium permanganate solution first, and then fill it with your potassium permanganate. And then pipette 25 milliliters cube of your Fe2 plus solution into a conical flask and place that on a white tile and then start your titration. So perform titration, adding potassium permanganate from the burette until the first permanent pink color appears. So that's how you'd actually carry out the titration. You're going to record your results in a suitable format. So that means drawing a table and having a trial titer and having initial and final volumes, and having a titration 1, titration 2, if required, further titrations, concordant results, i.e. Titer volumes within 0.10 centimeters cube of each other, and you're ready to use that data to do some calculations. Okay, so as far as concordant results go, within 0.10. Okay, so standard sort of titration sort of skills required. So we've got our data and we're now ready to do some calculations. We're now ready to work out how much iron there is in our iron tablet. So we look at the question set here, 24.3 centimeters cube of 0.02 mole per decimeter cube potassium permanganate. So that's our MnO4 minus. We should be able to work out the moles of that. Is reacting with 20 centimeters cube of our iron 2 solution. So imagine this iron 2 solution has been pipetted from your standard solution that you've just made. Okay, in the presence of sulfuric acid, and then we need an excessive sulfuric acid to allow the oxidation to happen all the way to Mn2+. Calculate the concentration of the iron 2 ion. Okay, so we can do that, of course. We're going to start by working out the moles of our MnO4 minus, and we know that concentration is the number of moles of the volume in dm cubed, so concentration times volume in dm cubed, so 0.02 is our concentration times the volume, which is 24.3 over 1,000. Okay, so that should give us 0.0243 times 0.0243 times 0.02. That gives us 4.86 times 10 to the minus 4. So 4.86 times 10 to the minus 4 moles. Okay, so that's what we're going to be using. We also need the molar ratios. If we go one screen back and we'll scroll down to the very bottom, the molar ratio of Fe2 plus MnO4 minus is 5 to 1. Okay, so Fe2 plus to MnO4 minus is 5 to 1. 2 plus to MnO4 minus is 5 to 1. So that's our molar ratio we need to use, and that allows us to work out the number of moles of Fe2 plus in our 20 centimeters cubed. Mole of Fe2 plus in 20 centimeters cubed is going to be 4.86 times 10 to the minus 4 multiplied by 5. I'll do that on my calculator. That gives me 2.43 times 10 to the minus 3. Okay, so in this question, we're asked to say what the concentration of our iron 2 in our 20 centimeters cubed is. The concentration would be 2.43 times 10 to the minus 3 divided by 20 over 1,000. That would give us the concentration. What if we wanted to find out the mass of Fe2 plus? Okay, so that would be, so the mass of Fe2 plus in 20 centimeters cubed would be pretty straightforward. It would be okay, so that would be so we know that the number of moles is equal to mass over the relative atomic mass. Okay, so if we want the mass, it would be the number of moles times the relative atomic mass. And so that would be moles times AR. Okay, so that number of moles multiplied by iron's relative atomic mass, which is 56 off the top of my head, I think. We can look it up very shortly. Should give us the mass of our iron. Okay, so moles equals mass over AR, so our mass is equals AR times moles, as we've got down there. If we were looking for the concentration, it would be, of course, concentration would be equal to the number of moles over volume in dm cubed. Okay, so that's how you would go about carrying out so the titration, redox titration, to find out how much iron there is in a given sort of amount of iron tablets. So assuming we worked out the mass in 20 centimeters cubed, we could then scale back up to the total volume in our volumetric flask. If, for argument's sake, we find the mass in 20 centimeters cubed and need to know the mass in 100 centimeters cubed of volumetric flask, then you would be multiplying that mass by 5 to get the total mass contained or dissolved in your volumetric flask. Of course, that total mass you can then divide by the number of tablets that have to be ground up, and that would give you the mass per tablet. Okay, so a pretty straightforward calculation if you're methodical and logical about it. There's one other question we want to very quickly look at, sort of in the same vein. So it's calculate the percentage of iron in a sample of steel wire if 1.51 grams of the wire was dissolved in excess sulfuric acid and solution made up to 250 in a standard flask. 25 centimeters cubed of the solution is pipetted into the conical flask and needed 25.45 centimeters cubed of 0.02 mole per decimeter cubed potassium manganate for complete oxidation. Okay, so let's have a go at doing this then. So if we use our highlights to pick out the different pieces of information, 25.45 centimeters cubed of 0.02 mole per decimeter cubed potassium manganate. Okay, so we can work out the moles of that, right? So we also know that 1.51 grams of the wire was dissolved and the solution made up to 250. So we've got 1.51 grams dissolved in 250 in the standard volumetric flask, and 25 centimeters cubed of that solution was pipetted out to use in the titration. Okay, so first thing to do, just as we saw in the previous question, is to work out the moles of permanganate. So moles of MnO4 minus is equal to 0.02 times 0.02545, and that should be equal to 5.09 times 10 to the minus 4. Okay, so that's the number of moles of MnO4 minus we've got. We do know what the molar ratio of MnO4 minus to Fe2 plus is. Okay, so we're going to assume here that when you dissolve your iron in sulfuric acid, what you get is iron 2 sulfate. It might be that a small amount of that has oxidized up to Fe3 plus, but we're going to assume that it's all Fe2 plus. So in this calculation, so MnO4 minus, that would be 1 to 5 as we saw in our previous question. So we're looking at 5 of iron to 1 of MnO4 minus. Okay, so that's our molar ratio. And so moles of Fe2 plus in what volume? That would be 25 centimeters cubed, is going to be equal to 5 times 5.09 times 10 to the minus 4. Which is 2.545 times 10 to the minus 3. 2.545 times 10 to the minus 3 moles. Okay, so that's how many moles we've got in 25 centimeters cubed, right? So what we need to do now is scale back up to see how many moles we've got in 250 centimeters cubed. Okay, we know how many moles are in 25. We can easily work up or scale up to get how many moles in 250. Okay, so number of moles in 250 must be equal to 2.545 times 10 to the minus 2 moles. So that's 10 times the amount you've got in 25 centimeters cubed. Okay, so having done that, we know, so let's calculate the percentage of iron in a sample of steel wire of mass 1.51 grams. So we can work out what mass this is equal to. So mass in 250 centimeters cubed, mass of iron, I should say, should be equal to, as we saw previously, it would be the AR of iron times the number of moles. So we've got 2.545 times 10 to the minus 2 times the AR of iron, which will round to 56. And that should give us 1.43. Okay, so 1.43 grams. And so if we want the percentage of iron, so the percentage composition in the steel wire of iron, it's going to be 1.51 times 100. Answer 1.51. And that gives us 94.4%. Okay, so those are the style of calculation that you would be required to do. And hopefully you found it reasonably straightforward. So this is the bits of where we're dealing with processing the data, to analyzing the data you've got from your titrations and making sense of it. Okay, so as far as the accuracy of this investigation goes, you want to ensure that you are using a pipette and a burette and a volumetric flask, so volumes of solutions is incredibly important. You also want to make sure that you're using an excess of the acid. If you don't, you're going to be forming a brown sort of sludge of manganese oxide, which makes it difficult to see the endpoint, and so you're liable to add too much manganate and nickel too large in volume. And then you want to ensure that you're repeating to get concordant results, so ensuring that your process is reliable. You then want to make sure that you apply the same process to the other tablets from the different manufacturers, for instance, so that conditions are the same in all the sort of different facets of your investigation. And then finally, having written up your report, make sure that you are including your citations, your references for the different sources that you've used. Make sure that you're comparing what you've got with what is already published and commenting on this. Okay, so that brings us to the end of this session. I hope you found it useful. Certainly, if you do have any questions for me, please drop me a line at boostrevision.com, and I would be more than happy to answer your questions for you. Before I sign off, I'm just going to have a quick check that we don't have any questions from our followers on YouTube. Okay, so there are no questions. That brings us to the end of today's session. Do you go away and tackle some of these sort of redox titration calculations that you've seen, but also do you go back and review all the different steps that we have used in order to sort of successfully sort of investigate the amount of iron in our iron tablets. Thank you very much for joining me. Have a great weekend, and I will see you soon.